Hello everyone. In this video, we are going to give a proof that the well-ordering principle is equivalent to the principle of infinite descent. Alright, so first let's familiarize ourselves with both of these principles and just their statements. So the well-ordering principle, which I may abbreviate as WOP throughout, says that every non-empty subset of the natural numbers has a least element. So the important thing to note here is it's only non-empty subsets, so we do not want to consider the empty set there because it has no elements at all, so how could it have a least one? And then the principle of infinite descent, which I'll probably put POID for, there exists no strictly decreasing sequence of natural numbers. So again, by strictly decreasing, we would mean that if our sequence is AN, that AK is always greater than AK plus 1, right? That the next term in the sequence is always smaller than the one before. So intuitively, you can see that these things are probably related, right? That, okay, if we don't have a strictly decreasing sequence, then that means they kind of have to have some lower bound, right? And so this should be somehow corresponding to a least element. And if a non-empty subset has a least element, well, if you take a sequence to be a set of elements, a set of natural numbers, then if there's a least element, it cannot keep decreasing forever. So this is kind of the intuition behind these two things being equivalent. So now let's go ahead and actually prove it rigorously. All right, so let's go ahead and prove it. So we are going to prove both directions actually by contrapositive. So we're going to start here by showing that the well-ordering principle implies the principle of infinite descent. So if we want to do the contrapositive, what we're really going to show is that if the principle of infinite descent is false, then the well-ordering principle is also false. So what does this mean? Well, we want to show then that, again, if the principle of infinite descent is not true, that is, if there is a strictly decreasing infinite sequence of natural numbers, then the well-ordering principle is not true. That is, there does exist a non-empty subset with no least element. Okay, so this is our goal for this direction. So let's go ahead and start, right? So we assume that we have a strictly decreasing infinite sequence. So suppose this sequence of natural numbers AN is strictly decreasing, where each element is a natural number, right? So this is a sequence of natural numbers, strictly decreasing. Then we need to find a non-empty subset with no least element, right? So we get to choose our subset. And since we have the choice, we're going to let S be, well, what doesn't have a least element? We know this sequence keeps going down forever, right? It's strictly decreasing. So the subset of elements in this sequence can't have a least element, or else it would be bounded. So let S be the set of AN such that N is in N. And so this is exactly just the elements that show up in our sequence, right? There could be a lot of repeats. This captures that, doesn't double count them or anything. Then, well, S is clearly non-empty, right? Because we have a sequence. And S has no least element. So we should justify this. So why is this true? Well, what does any arbitrary element look like in S? So since for any, say, AN in S, we know that since it's a strictly decreasing sequence, AN plus 1 is less than AN, right? This is true for any element in S, and thus there is no least element. You can always find something below it. So that takes care of this direction. So now let's look at the other direction, right? So again, we're going to go by contrapositive. So we want to show that if the well-ordering principle is false, then the principle of infinite descent is also false. So what does that really mean? What are we trying to show? So again, if the well-ordering principle is not true, this means that there exists a non-empty subset S of the natural numbers with no least element. And then for the principle of infinite descent to be false, then we would want to show that there results in some strictly decreasing sequence of natural numbers. So how do we actually show this? Well, we start by assuming we have this non-empty subset with no least element, right? So let S be a subset of N with S not empty and with no least element. Okay. Then our goal, just like in the previous direction, right, we created a set given a sequence. Here, we need to create a sequence given this set. So first, we note that, again, this is non-empty. So we know that there exists some element, right? So we know there is some, let's go ahead and call it A1 because it's going to be the first term of our sequence. So this exists because S is non-empty. Okay, and now, moreover, we know that A1 is not least. So since A1 is not least in S, that means there must exist some A2 in S that's less than it, right? And so once we know this, right, so A2 is in S with A2 less than A1, then we can just keep iterating this process, right? So continuing for any AN in S, there exists, again, AN is not least, and thus there exists some AN minus 1 or N plus 1 in S with AN plus 1 less than, strictly less than AN. And thus, this sequence that we've created, right, this sequence of elements AN, where each AN is in S, is strictly decreasing. And of course, S was a subset of natural numbers, and thus this is a strictly decreasing sequence of natural numbers. And so we have finished up our proof.